There. Let's go here. Let's close that. Let's slide that over. Good morning, Ryan. Welcome to Fifth Hour, Ethan. Let's see here. Cameron, Kellen, good morning. Ashna, Danielle, Annabelle, good morning. Rory, hi, good morning. I'm working from home today, so let me know if things get wonky on your end. Hello, kitty. At least I hope it was a cat. If it was a person, that person has a serious genetic defect that needs to be addressed immediately. I'm not judging, just saying. Let's see. Jeremy, good morning. Willa, good morning. Gabby, hi. It's nice to see your faces again. Miguel, and Josie, Jesse, and Jack. All right. So my hope is you can see the Pear Deck slide or the Pear Deck code. So go ahead and log into that, please. We'll need those slides today. Not seeing people log onto the slides. Are you having problems seeing the code? Could I get some feedback to just to make sure you can see the Pear Deck code this morning? Okay. All right. Oh. Okay. All right. Well, hi. Going through a lot right now. So I'm going to try to be as present as I possibly can with you this morning. But I ask for your grace and your kindness. For those of you who reached out, I appreciate it. It's not over at all. It's really just beginning. But I'm going to try to do what I can to the best of my ability with all of you for as long as I can. So in a moment, I will do our check-in, and then we'll dive into this idea that I hope you got a chance to explore with the Edpuzzle video, the Amoeba Sisters video for today, on the concept of Hardy-Weinberg equilibrium. Really briefly, before we explore it today, it's a way to quantify evolutionary change over the course of time by purposefully studying how a population's gene pool changes over the course of time. So obviously I've been providing some asynchronous learning opportunities for you, and you may have some questions about those that we need to answer first, and that'll be totally fine. But if not, we'll do a review of what you saw in the video and then answer any questions that you might have about equilibrium. And then spend most of our time together today looking at practice problems in small groups, that I can support in problem solving as you encounter each of the individual problems. And we'll end with our exit slip. So before we get started, is there anything that I can do for you? Any questions that you have? Anything that I can do to make your lives a little bit easier or a little bit happier right now? So I'm still not seeing anybody logged into the Pear Deck slides. Are you able to see them on your end? Okay. Excellent. Thank you for that. All right. Well, the check-in for this morning is quite simple. It's just a moment of silence, an opportunity to breathe, something I've been doing a lot recently. So it's really simple. I would just ask that you find a comfortable position. You can close your eyes if you want to, but you certainly don't have to. And just take 3 deep breaths and bring yourself into this moment as best you can, which is what I'm going to try to do as well. So, okay. If you did that, thanks for doing it. And if you didn't, that's okay too. All right. So you've had a chance, I hope, to watch the Edpuzzle video. I also hope you had a chance to do the asynchronous lessons. But before we jump head first into this idea of quantifying evolutionary change, what questions do you have before we get started? Whether it's about alleles and genes, or the different forms of genotypes, or the concept of a gene pool in general, anything and everything is up in this fair game right now. You can put it in the chat, you can unmute yourself, whatever works best for you. Or are you ready for the next step? Thumbs up if you're ready. Clearly, I've already skipped a slide here. So if you think you're ready, let's find out. I've got a simple practice problem. It's a formative problem, right? So it's practice. And I'm going to give you control of the slides. And there are 3 different practice problems on 3 successive slides, consecutive slides. So take a few minutes here and see if you can apply your understanding of what you learned in the video last night or the night before, whenever you watched it, to see if you can solve each of these questions, and then we can go over any or all of them when you're finished. I'm thinking probably 3 or 4 minutes to answer the 3 questions, so I will check in with you at about 9:12. Okay, go to it. And of course, if questions come up along the way, don't hesitate to ask.
Mr. Bergeron,
Mhm.
to calculate this, don't we have to know like the genotypes? Like if it's big A, or big A and little a?
So it's a really good question, a really important question. Are there any genotypes of the pigs that you do know for certain?
Um, no.
You do actually. What's true about the black pigs?
Their coat, they have a coat that's recessive to the pink coats.
Right. So, I mean, I'm not sure what it looks like on your screen, but on my screen, I've got pink pigs and I've got black pigs. So
Yeah.
the black color is recessive to the pink color. So in order for a pig to be recessive black, what must their genotype be?
Oh, homozygous recessive.
Yeah, way to, it looks like
Wait.
you may have even used your note. That's awesome. And you can use whatever letter you like, right? We're just using the letter as a symbol for the allele, really for the gene or the type of the version of the gene that we're working with. So maybe you want to use these for black. It doesn't matter. But you do know the genotypes of the black pigs in this problem.
Okay, I get that. Thank you.
Of course.
So are there 2 alleles per pig or just 1?
So we would say that each pig, really each living thing, is going to inherit 2 alleles, right? A version of a particular gene from each of their parents. So every pig should have 2 alleles. The type of allele might be different, right, depending on the pig, but each should have 2. Good question.
Okay.
So I'm trying to address the chat while you folks are working. I hope that's not too distracting. But one of the takeaways I hope you made from the asynchronous lessons from the last couple of days is that the term allele is simply used as a descriptor for a version of a gene. And you probably have heard the term gene before. You may have even heard the term allele before. But the terms that we use to describe um, these entities, for lack of a better term, it's really, 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 really important for biologists. And often we get really lazy when we describe alleles and genes. We actually describe them as being the same thing when they're definitely not the same thing. An allele is a version of a gene, and right now we're keeping it pretty simple. They really come in 2 forms, like a dominant form or a recessive form. And in general, the gene is going to provide the instructions that a cell uses, really a set of DNA instructions that a cell will use to build a protein. We're also keeping that definition really simple as we get started here. So an allele is a version of a gene, and a gene is a set of instructions that a cell uses to make a protein. So we can almost think of the alleles as being different versions of instructions that cells use to make proteins. All right. So it's 9:12. Let me do a quick check-in here. How much more time do you think you need to finish all 3 questions just with finger minutes? Each finger is a minute, a fist is 0. And for those of you who have your cameras off, if you could either turn them on quickly or put something in the chat, helps me get a sense of how much more time everybody needs. Seeing lots of 2s and 3s, so maybe just 2 more minutes and we'll check in again at 9:15. If you feel like you've already got a handle on this, since you're in student mode, if you want to click ahead to some of the practice Hardy-Weinberg problems, kind of challenge yourself a little bit, you're welcome to do so. You could also just look at the notes that we were going to quickly review on Hardy-Weinberg equilibrium, if you'd like. But we'll come back together here in a couple minutes and go over these problems if that's helpful. And keep asking those questions. Thank you for those of you who have already asked. It's really helpful to me, and I think helpful to the group as well.
Just to make sure, are we supposed to be calculating this using the what's it called, Hardy-Weinberg equilibrium equation, or for like the first 3 questions, do we just count, and use math?
So really good question. Again, thank you for asking. I think what you're going to find is that you have to use those equations, those simple equations to solve these problems, because especially when you get to the pink pigs, kind of going back to your original question, Jesse, you don't know the genotypes of the pink pigs.
Okay, so the numbers that we're supposed to get for like the dominant and recessive alleles,
Alleles.
how do you say it? Alleles, are they supposed to add up to 1 then?
The numbers of the alleles won't add up to 1. One of the takeaways I hope you saw from the video was that it's the frequency of the dominant and the recessive alleles that are going to sum to 1, or the frequencies of the genotypes in the population that will sum to 1. So we're not going to have a sum here where the number of recessive alleles equal or plus the number of dominant alleles equals 1. However, maybe you've already noticed there are 16 pigs in this population. And I think it was Jack who may have asked, but I missed it. Maybe it was Jeremy. That means there's 32 total alleles in this population gene pool. So whatever numbers you come up with, they should sum to 32.
Okay, I got it. Thank you.
So it's a little past 9:15 now. Would it be helpful to go over these problems together? Thumbs up, thumbs down, don't really care. Seeing a lot of thumbs up. Okay. All right. So we will certainly go over these, and we'll just kind of go over them in order as we do so. Okay. I really thought the Amoeba Sisters did a good job with their Hardy-Weinberg equilibrium video. And one of the reasons why I really like it is they use the same terminology that I've used for years, but their video is new. So I was really excited to see that they were using terms like Hardy-Weinberg equilibrium is dependent upon a set of assumptions that are never, ever, ever going to be achieved, ever. It's literally impossible to establish Hardy-Weinberg equilibrium. And yet we do what we do with these calculations to establish a baseline, a starting point, a time 0 to ask, okay, what does the population look like now? So that if we come back at some later time and we study the population again, is it different? And if it's different, that means one of those assumptions, and we can go over those assumptions in a few minutes if that would be helpful, has been violated, right? Because we're no longer at equilibrium, we're at disequilibrium because the population has changed due to some factor, maybe genetic drift, maybe natural selection, maybe mutation, maybe immigration or emigration. We don't know until we study the population in more detail, okay? So everything that we're about to do with these practice problems involves calculations that are establishing the baseline, the starting point for the population, so that we could come back to it and explore it and study it later. All right, so hopefully my pen will work here. Let's find out if it does. So we've got 4 black pigs, okay, and sorry, I'm using my trackpad here. And if you counted, that means we've got 12 pink pigs. Okay. So to speak to Jesse's question from a moment ago, if we were to assume that this population is at equilibrium, and really that's the only place you could start, right? What that's telling us is that of those 4 pigs, right, 4 out of 16 of them are black, right? And since the black color is the recessive color in this case, that 4 out of 16, excuse my penmanship here, that's going to equal the Q squared term in the Hardy-Weinberg formula. Okay. So the math is not going to be too complicated here, right? 4 out of 16 is 0.25. We can probably even do this in our heads, which means Q oops, hopefully you can see that. Sorry. Q equals 0.5, okay? And since P and Q have to sum to 1, that tells us that, sorry, I can't really do decimal points with this pen very well. Hope you can see that on your end. That means P also has to equal 0.5 because P plus Q, the sum of the allele frequencies in the population, have to equal 1, okay? So what this is telling us is that the number of recessive alleles, right, in this case, sorry, the frequency of recessive alleles in this case is going to be 0.5. So now we can begin to do some work, right? And we can begin to tell ourselves or ask ourselves, okay, well, if 4 out of the 16 pigs are black, and each of those black pigs is bringing 2 black alleles, 2 recessive alleles into the population, okay, then we've got a total of 8 black alleles coming from those 4 black pigs, okay? To speak to Jesse's question from a few minutes ago, okay, well, what about the pink pigs, right? They're not black, they're pink, right? So they have the dominant trait in this case. But you can have the dominant trait, the dominant characteristic, and have either a homozygous dominant genotype, no recessive alleles there, or a heterozygous genotype and have 1 recessive allele there. But I can't look at a pink pig and know if it's homozygous dominant or heterozygous. But with the Hardy-Weinberg equilibrium equations, I can make some assumptions as to what that population does look like, given what I've done so far with my allele frequency calculations, okay? So if I'm focusing on the number of black alleles, I don't care about the homozygous dominant pigs, right? I don't care about the P squared term. What I care about is that 2PQ term, because the 2PQ term in the formula is relating back to the heterozygous genotype frequency in the population, okay? But I've already calculated P and Q, so the math is going to be pretty simple. It's just 2 times 0.5 times 0.5. So that's 0.5. So I'm going to pause there just for a second. How are we doing so far? Thumbs up, thumbs down. Okay, seeing a lot of thumbs up. Thank you for that. So again, I'm not focusing on the homozygous dominant pink pigs. They don't have a recessive allele, and I'm trying to count the number of recessive alleles, so that doesn't matter. I'm focusing on the heterozygous pink pigs because they have at least 1 recessive allele. So really what I'm trying to figure out is how many of the pink pigs in this population are expected to be heterozygous? Well, half of those pink pigs are expected to be heterozygous, okay? And there's 12 of them, right? There's 12 pink pigs, 16 pigs total, 4 of them are black, 12 of them are pink, and half of those pink pigs are expected to be heterozygous. So that's 6, excuse my pen here, 6 heterozygous pigs. And each of those heterozygous pink pigs is bringing one recessive allele, right, to that population. So I've got the 8 black alleles from the 4 black pigs, 2 black alleles per pig. I've calculated, or I expect, based on my calculations, that I've got 6 heterozygous pink pigs that are each bringing one recessive allele to the party. So all I've got to do is sum those together. 8 plus 6, there should be 14 black alleles in this population.
Wait, why is there 6 heterozygous?
Well, there's 16 pigs total, right? So if there's 16 pigs total and 4 of them are black, 12 of them are pink. So of the
half
pink,
pigs. Okay, I get it.
all right.
Is the 0.5 not out of the total population?
Well, Isaac, you might already be noticing something that's really important, right? We just calculated 14 black alleles, right? But when we go back over here, right, we might expect, if there's 32 total alleles, right, there's 16 pigs total, that half of those alleles, that 16 of those alleles are black, but only 14 are showing up as black. That's telling us this population is not actually at equilibrium. The numbers don't match. And when they don't match, that's actually telling us something. It's a little bit of an advanced concept, an advanced understanding, but it's one that's just worth mentioning as we get started. Should we try the next one? Is it okay if I clear out this ink? Of course, I'm curious here. Look at that. Lots of 14s, or close to 14s. Okay. Not too bad. All right. Well, the second one, we've already done a lot of the work, right? If we expect there to be 14 black alleles and there's 32 alleles total, well, 18 of those alleles are expected to be dominant, right? I guess pink, if you like. All right. So, oops, I don't have my pen up. So that would be 18. Whoops, sorry. Take out a student mode here real quick. Huh, that's weird. Can't see your answers to that question. That's okay. But that would be sorry, my brain isn't working very well this morning. If there were 14 black alleles, there should be 18 pink alleles or dominant alleles in the population. And we've actually done some of the work for part 3 already as well, right? Predict the number of pigs with a heterozygous genotype. Well, if I pull up my ink one more time, remember that 2pq in the Hardy-Weinberg formula refers to the frequency of the heterozygous genotype, right? And we went to the trouble of calculating P and Q based on the number of black pigs in our population. And both of those, you can really not do decimal points with this pen very easily. We're 0.5, so 2 times 0.5 times 0.5 is 0.5. So half of the pink pigs are expected to be heterozygous in the population, which would work out to 6 of those pigs. Okay. So before we move forward, what questions do you have about any of these practice problems? They're weird the first time you do them. So if you're feeling a sense of disequilibrium, that's okay. Is it okay to move on? Thumbs up if it's okay. Thank you, Natalie. Thank you, Rory. Isaac. Let me erase this again here real quick. Back to my mouse. All right. So really what we're trying to do with all of these calculations is we're trying to quantify, to mathematically determine whether or not evolution is taking place within a population over the course of time, right? So in many ways, if we think back to what we were looking at last week, right? We've got that common ancestral population. It becomes isolated in some way, right? Reproductively isolated. And then something like natural selection might begin to act on those two populations. Or now, maybe something like genetic drift begins to act on one or both of those populations. Heck, sometimes the act of isolating that original population reproductively, whether it's through geographic isolation or some other form of isolation, that mechanism actually leads to genetic drift, right? A random change in the population that has nothing to do with natural selection. Okay, but regardless, what we're trying to do is once that population becomes isolated, we're trying to measure how it's changing. Specifically, we're trying to measure how its gene pool is changing in respect to the presence or absence of particular alleles in that population over time. And if those allele frequencies are changing, that population is not at equilibrium. It's evolving. However, the opposite, if those frequencies are staying the same, the population is at equilibrium and it is not evolving. Okay. So pausing there just for one more moment, is that bringing any new questions to light for you? Sorry, I'm trying to monitor the chat too. There's nothing in the chat. Okay. All right, so hopefully I don't need to recapitulate what you learned in the video. If you haven't had a chance to watch the Hardy-Weinberg video by the Amoeba sisters, I would strongly encourage you to take a look. I think it's really helpful. I think they really do a good job. And it's cute. I mean, come on, it's cartoons. But there are two equations that you're going to want to be familiar with. And when I say familiar, that's not memorized. I even tried to add in the image from the actual AP Biology formula sheet into the video, into the Edpuzzle video, to show you that the equations are built into the formula sheet. You do not need to memorize these, okay? But there's two that are important, and they're often confused. So just really quickly, the first formula is P plus Q equals 1, where P and Q refer to the frequency of the dominant and the recessive allele in the population, respectively, okay? And they have to sum to 1. The second equation, P squared plus 2PQ plus Q squared equals 1, refers to the genotype frequencies. So like the genetic background of the individual in the population. They are fundamentally different equations. They're telling us different things, okay? But they're often confused. Students often confuse the allele frequency formula for the genotype frequency formula or vice versa. So as you practice here in these next 20 minutes or so, I would encourage you to think to yourself, what equation am I using and why am I using it? Okay. So again, pausing. Questions, comments about any of this so far? Okay. So two formulas, and then these are the requirements for equilibrium, right? These are the requirements that have to be in place for a population to not be evolving, right? So whether we're focusing on one population and how it's changing over the course of time, sorry, somebody just popped in here, trying to let them in. Oh, now they're gone. Or we're focusing on following reproductive isolation, that one population has been split into 2 or more new populations, and we're tracking to see how those populations have changed over time. Always want to try to connect it to our previous learning. These are the requirements that have to be in place. But to be honest with you, they're never going to be in place, right? How am I going to get a large population that doesn't have any mutation taking place, right? That's mating randomly. I mean, think about that one in and of itself for a second. Random mating. No selection of mates? None? No Tinder? No Match.com? No OkCupid? Nothing? It's ridiculous, right? It's never going to be established, right? And then no natural selection? No characteristic is favorable over any other? And then we're going to keep the populations isolated in a way that nobody moves in and nobody moves out? That sounds like fun. That sounds like prison, right? It's not about these requirements being met, and that's why it's not about memorizing these requirements. It's about understanding that we're making the assumption as biologists that at this time point, all of these things are in effect, even if they're not, right? We're making that assumption at that particular time. We're doing all of our calculations, and then we're asking at some later time point, have those values changed? And if they've changed, it has to be due to at least one of those factors and probably more. And that's the job of biologists, to figure out which of those factors has influenced the population over time. Okay. So before we take our break, questions, problems, concerns, conundrums. All right. Well, let's take a short break then, and then we'll come back in small groups and try to tackle some of these practice problems. And we'll save some time at the end to go over at least a few of them so that you have some comfort and confidence with solving these sorts of problems before you leave. Okay, I've got 9:35 on my clock, so let's come back in 3 at 9:38. right. If we could start making our way back together. All right. So we've got just about 17 minutes left in class. So in a moment, I will do two things. I will put the slides back into student mode so that you can drive. And I'll put you into a breakout group with one or two other people. And I would ask that you try to solve some of these Hardy-Weinberg problems using what you learned in the video and what we just did a moment ago. And then maybe we'll do that for about 10 minutes, and then we'll come back together and we'll use the last 6 or 7 minutes to solve one or two of the problems that you had a chance to look at. I will say that if you're interested, the answers to these questions, Pear Deck won't let me post the answers to the questions live. But if you want to check your answers, you can go to the Unit 3 notes on Google Classroom, find the question, and in the speaker notes, the answer should be highlighted if you're curious. So you're welcome to do that if you'd like. But it's just about 9:39, so I'm going to put you into those breakout rooms. Please don't hesitate to call me in if a question comes up while you're working on a problem or two. And again, I'll put the slides in student mode so that you can choose the questions that work best for you. Here we go.
So you can just square that 0.11.
Is that true?
Is it? I don't
Answer
know.
between 0 and 1 expressed to the nearest hundredth. Okay.
You said that the answers were on the slides, and they are not on the slides.
You have to like go to the like Google Slides that like I don't know.
I did.
Oh, you did? The speaker
Yeah.
notes. In the speaker notes.
There, all it says in the speaker notes is this is a Pear Deck slide. That's all it says.
Okay, well.
Maybe if I click on this. Oh no, that's not it.
I can fix that if you really can't
Oh.
see it. It's not a big.
Oh,
All right.
I know I did it. If you can't see it, it's easy to fix.
Okay.
I'll double check. But thank you.
I didn't even realize he was in
I
here with
didn't.
us.
Did not see it.
Okay, next problem. Researchers observe a large population. Okay.
So
Calculator. Okay, here we go. On. Clear. 1759. This is a TI-15. Oh my god.
I have the X I think everyone had.
I actually never got a graphing calculator.
Never got a graphing. I thought you had to, like legally.
You
You had
did.
to. Well. Then, oh yes, we got the answer right.
Oh, good. You can see it. Okay, good.
Yep.
I'm updating it live. So good. All right. Excellent.
Thank you.
Keep going here.
Okay.
Wow.
This is TI-15 is gross. Doesn't work.
What is it? What does it look like?
Can you see
Oh, that's the TI. Yeah. Yeah, I know.
that? Oh my god, it's so big and it doesn't do anything correctly. Okay, 1,759 divided by in parentheses.
0.14 is Q. So P is
0.14 is
yeah. 0.86.
square root that is 0.37.
What?
I got because
2 times.
isn't 0 point whatever. Okay, wait. Square isn't 0.14. Isn't that Q squared?
No, I think that's just. Yeah, it is.
Yes, it is. Okay.
Yeah. No.
Because if you square root it, it gets to like
Yeah.
a pretty even 0.37.
Yeah. It was. Okay.
So then the other one is 0.63.
Yeah. I don't know how I did all the other ones and then I just blanked on this one, but that's fine.
0.63 square root is 0.79. What proportion of future population, especially with the
Okay. Because I just did 2 times 0.37 times
yeah.
0.63. 0.47.
Well, no, don't you have to square root 0.63?
No, shouldn't that be the actual frequency? Because we've already square rooted.
Oh yeah,
0.1, yeah. I think
Okay.
that's the actual frequency.
Okay, so what was the answer?
0.47. Oh,
All right.
and
Is that what
did
it
we
says
get
on
it
the-
right? No, that is not what. Oh wait, yes, it is what this is.
Okay, good.
Yeah. Oh, there's someone else in the room. Danielle is in the room.
I know.
I just noticed. Hopefully, she's been solving it alongside us. All right.
I have. I
Okay,
swear.
that's good. Okay.
All 3 alleles.
This is
This is just
how
impossible.
could we do
Let's
this?
just not even try it.
Except that I think it's actually just. Wait, is it 3 alleles or is it just is one of them just the heterozygous one? Oh, it's codominant. Is that the same equation then?
The equation's at the bottom. Assuming the population is frequency of the I allele. What's the I allele?
I allele is, I think they're all I's, but I guess
Oh. Wait.
how is I so common? How is O 0.45? I guess this just probably isn't real.
I think the I allele is just A, B, and AB. I don't think it's O.
Yeah, you don't. Wait, where does it say I allele? Oh, what is the frequency of the I? No. The I allele is O.
Is O?
Yeah, that's the letter I. Is used for the lowercase I is used for O.
Oh, I didn't know that.
Can you? It's in the chart. It's in the chart.
Oh, are those L's? Oh wait, are the
That's a,
oh, is that a 1? I know like the type O it says I, but what are the things above that? Those aren't I.
oh, I think those are uppercase I's because they're dominant.
Okay.
'Cause they're
Okay.
So this is
So is it just 0.45? No. Is it the
no,
square root of
because type A
0.45?
and type B can have an I, have an I allele.
Oh.
So we gotta use this big equation over here. So 0. I think you can square root 0.45, right? Because it should be the same.
All right, so as we come back together here, let's try to pick a problem that we can wrap up class with together. Doesn't matter which one. Uh-oh, you're gonna hear my kids run into the room. Get ready.
Dada, my flower break.
Oh man. You got some good flowers though.
I got one.
Okay, I gotta teach the kids, okay? So
No.
guys.
Ben and Celia. You're saying
right.
hello.
Welcome to my world.
You're saying hello.
Well, we're doing the best that we can here. All right. Well, this is Ben. If you wondered that if genetics was real or not, it is.
There was anybody talking.
No, they don't talk.
Why?
It's a good question.
Why do
Maybe they'll talk to you, Ben. Maybe they'll.
Hello, he's calling us out.
Hi, Ben.
All right. Is there a problem that we could talk about?
Oh.
Uh-oh, his flower
The
broke.
blood type one.
The blood type one? Yeah.
What the flower? This petal back on.
Well, these things happen, pal. It's okay. Can I see? Can I see? I bet I can fix it once I'm done, okay? All right. The blood type question, if you got to it, this is a question that drives students crazy. And the year that it was actually, so all these are AP questions. They're from released AP exams. And I can tell you that when this question was asked, let's just say it did not go well. And it's interesting because it's actually not that complicated once you look at it. Because in this case, you've got, oh, buddy, you can't push buttons.
I just want.
Once I'm done, you can push some buttons, okay?
Okay.
So the key to this problem is to focus on the genotype or the blood type that you know has a defined genotype, right? And like any problem, and I thought the Amoeba Sisters did a really good job with this, that means you want to focus on the homozygous recessive genotype, which in this case is that type O blood type. Sorry, you were in student mode. Now you're back into teacher mode. Okay, so this is the problem, the blood type problem. And you're focusing in on that final blood type that has the known genotype, right? You might say, well, why not AB, right? It's got the IAIB genotype, but that IA allele could pop up in either of the genotype up above, and the IB allele could pop up. It's okay. It's okay. Not right now. How about Sheriff Kelly? Milk. Come on. I gotta wrap up. Okay. And the IB allele pops up in other genotypes. So the
I'll come and watch Sheriff Kelly in a few seconds, okay?
Okay. So what it comes down to is that this II, right? It doesn't really matter which of the P squared, Q squared, or R squared terms that you use. That's what you're going to solve for. That's the frequency, right, of this genotype, 0.45 in this problem. So all you have to end up doing is calculating the frequency of I, which again, you can assign as any of these variables. Probably makes sense to assign it as R. So the square root of 0.45 equals R. And then it's just a matter of, well, really that's all you're asked for in this problem. So that ends up being the answer to the problem. So it looks really complicated at first glance, but in the long run, it's not that complicated at all. Okay. All right. So I do want to honor the time that we have left and this tiny human on my lap right now. So before you go, if you would, drag your dot. Really thinking about our next steps. Next time we meet.
How red?
Ben says red, so obviously he's an expert. And if you don't drag it to red, that means a 3-year-old is superior to solving these problems compared to you. But he's my son, so honestly, that shouldn't be that surprising to you. Right.
He dragged red.
Let's see where we are. Let's see where they are, Ben.
Red.
Couple of reds, quite a few yellows, and a couple of greens. So it looks like maybe we should start off with some more time on Friday when we meet again to solve some more of these problems. Okay.
And
Your only homework between now and then is to work on the take-home summative assessment number 2. Okay, which will go back a step to the content we've covered previously. Other than that, it is 9:55.
I don't have to tap red.
He says you have to tap red. I'm telling you.
Tap red.
So thanks for being here.
Tap
And
red.
apparently I'm gonna go watch Sheriff Callie.
If
you haven't watched it, it's an amazing show on Hulu. I highly recommend it. Voiced by by Mandy Moore, the songstress, the actress. So I'll see you in a couple days. Thanks for being here.
Thank you.
Thank you.
Thank you.
Thank you. Bye.
Some of them press the red button, yeah,
Some of them press the green button.
and some of them press the green button. Yep.
Some of them press the yellow button.
Uh-huh. Do you want to go watch your show now?
Yeah.
Okay. Thanks for hanging out. You all right? Come here now. Did you trip? I'm sorry. Oh, you gonna push the buttons? Oh, you were going so fast. Come here, you. Come here, you. Come here, you. You're... Do you want to see the next group of people come in? No. No. Oh man, I bet they want to see you. I bet they want to say, hello, how are you? How's it going? So many different things I'm trying to navigate all at the same time, I know. Look, that gigantic pear. That's funny, right? Where hurts, bud? You want to go watch? Let me carry you downstairs real quick to watch Callie?
Yeah.
Okay. Give me a second
Where
here.
is these buttons?
Well, be careful which buttons you press, okay? Because
I made it back to it.
you did. All right, you ready? I'll bring you downstairs real quick to watch some Callie. Because I have to get my next class started. You want to walk? You want me to carry you?
How do you fix my little pie?
Let me see. I got something in here to fix it with. Try the little piece of tape.
No, I don't want.
Well, then I'm not going to be able to fix it, buddy, because I have to get it to stick. Okay. So what would you like me to do?
You don't go with tape.
Well, there's some glue downstairs. You can ask mommy for the glue and we can fix it.
No, I don't need them.
Well, daddy has to teach the kids, okay? So either you need to go downstairs or you need to sit back in my lap. What would you like to do?
I want mommy.
What?
And my mom to go upstairs.
You're going to have to ask her, okay? Bud, daddy has to teach his class, okay? So I have to. Well, do I need to carry you downstairs?
No, mommy to.
Well, mommy's downstairs. She
I
doesn't know.
want to come up.
Okay, well, why don't you go ask her,
No, I won't. I won't.
buddy?
And it closed.
And daddy has to start his class, okay?
Now I want it to be closed.
Benjamin, I'm not kidding around. I have to be able to do my job, okay? You need to go downstairs or sit on my lap. You have a choice.
No, I'm choosing mom to come upstairs.
Bud,
No, mom to come
then
upstairs.
let me go get her.
No.
Oh my God, I need your help, please. She's walking up the steps. Daddy's got to do his job, okay?
What?
I know, that's what happens, honey. This is the only one, you are not the only one this is happening to. This kid's interrupting.
I know. I just need to be able to do my job.
I can't get the door.
It's fine.
Come on down.
Sorry, everybody. Chaos. So give me a second here and I will be with you in about 5 seconds. Miss anybody? Not yet. Okay. Well, I'm obviously working from home today. So can you hear me and see me okay? Give me a thumbs up. Thank you. And looks like you can see the Pear Deck code, so that's good. People are logging in. So keep doing that if you haven't had a chance to do so yet. Okay. Hello again. I'm gonna give this a shot. And I'm gonna try to keep it going as long as I can. But things are not okay on my side of the screen. And that's okay. Because things aren't always okay. But I'm here right now and here to help you and support you and hopefully support your growth as a learner for as long as I possibly can. So our agenda for today, we'll do a quick check-in really to ground ourselves in the moment, something I've been doing a lot recently. And then we want to jump into the content that was covered in the Edpuzzle video that I hope you watched before coming to class today. I thought the Amoeba Sisters did a really good job describing this new concept of Hardy-Weinberg equilibrium. Really, it's a quantitative way, a mathematical way of exploring evolutionary change over time. And it builds off of so much what we've done already in terms of natural variation and natural selection and speciation, even evolutionary trees for that matter. So I've got some different practice problems that we can look at over the course of the hour that I hope will build a deeper understanding along the way. And of course, if there's any questions that popped up as through any of the asynchronous learning opportunities that I tried to provide to you over these last few days, we can tackle those as well. All right. So before we get started, what questions do you have for me or for the good of the group? Well, the check-in today is very simple. It's an opportunity to breathe. And I've been doing this a lot recently. So what I would invite you in just the next minute is to find a position that you can be comfortable in. And if you want to close your eyes, you can, but you certainly don't have to. And just take 3 deep breaths. Okay. Is there anything that I can do on my end that would make your lives a little bit easier or a little bit happier right now? Did just want to offer my my appreciation for those of you who did reach out, um, or just maybe didn't reach out but sent positive thoughts, even prayers my way. I appreciate that. I do. Um, what I'm experiencing is far from over. But as I mentioned earlier, I'm here now, and my plan is to be here for as long as I can be. Um, and I'm going to take it moment to moment, hour to hour, day by day. So, all right. So the first practice problem, I'm kind of calling it Here Piggy Piggy. It's a formative assessment, so it's just practice. And it's a way for us to work with the content that I'm hoping you were exposed to through the Edpuzzle video. But I also know that there was some content that was introduced in the asynchronous lessons that I was posting that you might have questions about. So really there's 2 directions that we can take. If there's burning questions that you have about anything that you've seen over the past few days that we need to address, that's a great place to start. Or if not, let's go ahead and start in with this piggy practice problem. Anything we need to address? Gene pools, genotypes, alleles versus genes, terms you may be familiar with from middle school, but it's probably been a while since you've even had to think about them. You can put something in the chat. You can take yourself off mute.
If the, oh wait, never mind. I read the question wrong.
Are we ready to try some of these practice problems? Thumbs up if you think you're ready. Some people I can tell are reading the screen. I'm watching your eyes. Okay. Well, I'll just say before you get started, or if you have unless you have already gotten started, we're making the assumption that this piggy population is at Hardy-Weinberg equilibrium. So in order to solve this problem, you want to try to use the formulas that you were introduced to in the video. So here's what I'm going to do. I'm going to hopefully, oh, that's why. Okay. I'm going to put you into student mode. Okay. And there are 3 different questions. Okay. So you can tackle them at your own pace. I think only the first question has a spot to enter your answer. So don't worry about that. But I'm thinking probably 4 or 5 minutes to tackle the 3 questions. And so I'll check in with you at about 10:14. And if we need more time, that's fine. But if we're ready to go over them or any of them, we can do that too. And of course,
I have a
I'll be here.
question.
Of course.
So you said that we don't need to memorize the formulas, right?
You're not. You do
Okay,
not.
cool.
Yeah. So I tried to be really purposeful in the video. I literally cut and paste an image of the formulas that are part of the AP Biology formula sheet that's given to you as part of the exam.
When you're calculating the number of recessive alleles, isn't it like possible that some of the pink pigs have like one dominant and one recessive? Like, how do you calculate that? Like, how do you know?
So it's a great question. And you don't know, which is why Hardy-Weinberg equilibrium equations are so helpful to us. So would it be helpful to, I mean, you folks tell me what's best for you right now. Would it be helpful to tackle this problem together? Or do you want to take some time to answer it on your own? So if you'd like to do it together, raise your hand. If you want to do it on your own, give me a thumbs down.
Could we do like the first part together and then the rest of it alone?
Yeah, absolutely. Absolutely. So I'll have to apologize in advance if, sorry, I'm trying to monitor the chat here too. Together. The pen, the writing is going to be pretty messy, but I'll do the best that I can. I'm using my my trackpad and not my mouse because I'm at home. So please bear with me as we do this. All right, so if we do this first one, let me do a couple of things here. First, let me take you here. Let's take you out of student mode so that we're all looking at the same thing at the same time. And let me go back and get my drawing tools up. All right, so indeed, right, you've got this situation where you're trying to calculate the number of recessive alleles, and you're told that black is recessive to pink. But certainly there could be pink pigs, right, that are homozygous dominant, right? They have 2 copies of this dominant pink allele, right? But there could also be pink pigs that are heterozygous and have 1 copy of the pink allele, but 1 copy of the black allele, right? They have 2 different versions of this particular gene, the dominant version and the recessive version as part of their genotype. And you can't look at a pink pig and know if they're homozygous dominant or heterozygous. So this is where the formulas can become so useful. So what we do know about this really simple piggy population is that 4 of the pigs are black, and that black is recessive to pink. So maybe you've already done this, but there are 16 total pigs in the population. And if you don't believe me, you can count them up really quickly. Some are in the background, but I promise you there's 16. So that actually tells you something really important, right? That 4 out of the 16 pigs are black. And since black is recessive, 4 out of 16 is Q squared, right? Remember, Q squared is the frequency of the homozygous recessive genotype within the population. So to be black, you've got to have 2 copies of the black allele. You've got to be homozygous recessive, right? So we actually know that about the population. And then the math itself, what's great about these problems is that the math is never very hard. It's the conceptual application of the mathematics that we're trying to get to. But you can probably even do this in your head, right? That 4 out of 16 is 0.25. Again, I apologize for the handwriting here, or the, what is this? Pen writing, mouse writing, trackpad writing. But Q, clearly, yikes. Is 0.5. Right? So the frequency of the recessive allele in this population is expected to be 0.5, given what we've done so far. Okay. Now, one of the formulas that was, and Anna already mentioned this, that you don't have to memorize, right, is that P plus Q equals 1, that the frequency of the dominant allele in the population equals, the frequency of the dominant allele plus the frequency of the recessive allele in the population equals 1. So P plus Q equals 1. So if you know Q, in this case 0.5, you know P, in this case, is 0.5. Okay. So the number of recessive alleles in the population, given what we've done so far, we would expect half of the alleles to be recessive, right? Well, how many total alleles are there in this population? How many total pigs are there in the population?
16.
16. And each pig brings 2 alleles to the pig party, right, to the gene pool. Right? They inherit 1 from mom and 1 from dad at fertilization. So if there's 16 pigs, right, there should be 32 total alleles in this really simple population. And as a consequence, we expect half, right, Q equals 0.5, half of those 32 alleles to be recessive. So 16 are expected to be recessive. Okay. Want to try the next 2 on your own? They build, so they shouldn't be too hard. So now it's 10:16 and you've got 2 left. So let's come back together at 10:20, but I'll still be here for clarifying questions. I want to take you out of teacher mode here, put you into student mode so that you can drive, go at your own pace. Okay. And again, the next 2, they're not going to have a spot for you to record your answer. That's okay.
I got
Pause. Don't announce the answer until everyone's had a chance to do it.
No, and I mean I got something different for number 1.
Okay.
That's what I'm worried about. I got 14 alleles and not 16 alleles. I'm sure what I did wrong there.
So yeah, I don't know that you did anything wrong. In fact, you didn't do anything wrong. What's happening to this population is that this population is not actually at equilibrium.
Oh.
And we can talk about that. We can come back, we can circle back to that for sure. Okay. But for right now, let's try number 2 and number 3. And then we can always come back to number 1 and explore why you're coming up with 14, Ben. It's a really good observation. So Paige, I'm noticing that you're asking a question to the whole group. When you say the next one, do you mean number 2?
Yeah.
So in number 2, since it's a takeoff of what you did in number 1, right? Since you know P and Q have to sum to 1, right? The frequency of the dominant allele and the frequency of the recessive allele have to sum to 1. P is also 0.5 if Q is 0.5. So number 2 really is just the same mathematics, right? If there's 16 pigs, right? There's 32 total alleles. We would expect 16 of those alleles to be dominant.
Thank you.
And yeah. So it's the P plus Q equals 1 formula that you're using. All right, so it's just about 10:20. How much more time, if any, do you need to finish answering these 3 questions? Yeah, finger minute. 1 minute, and remember a fist is 0 minutes. If you have your camera off, if you could just turn it on quickly or post in the chat how much more time you need. That's super helpful to me. That makes sure that I'm not rushing anybody. Don't want to rush anybody. Trying to be responsive to your needs. I'm seeing some 0s, some 1s, some 2s. Why don't we just take another minute or so to try to answer the questions? And then we'll come back together. If you want to go ahead, since you're in student mode, feel free to take a look at the notes. Really, they're just a review of what you saw in the Edpuzzle video. And if you keep clicking, you'll get to some Hardy-Weinberg practice problems that are similar to the one that you saw at the end of the Edpuzzle video. So please use this time to practice if that's helpful to you. All right, so try to find a good spot to pause. And we'll come back together here. It's okay if you didn't get to all of them, or if you're confused, or if you're an expert. or all in different places in a journey like this. Alrighty. Bring you back up here real quick. All right. Would it be helpful to go over number 2 or number 3? We kind of did number 2 based on Paige's question. Would it be helpful to go over number 3? Maybe then just circle back to Ben's point too about, wait a minute, but I got 14. Or maybe you did too. And that's okay. Okay. I'm seeing some thumbs up. So move you back here and clear this out. So again, trying to draw on the screen to the best of my ability here. We said before on the previous slide, right, that P was 0.5 based on what we're seeing with those 4 black pigs. And Q was 0.5 based on those 4 black pigs, right? And as a consequence, we would say that the number of dominant alleles in this population should be half of the total number of alleles, 16 pigs, 32 total alleles. We would expect this to be 16, okay? So we would expect if the population was at equilibrium, all right? So is it okay to go to the third question? Okay. The final piece, right? Because, okay, same deal. Sorry, I keep opening this pen up, right? So if P is 0.5 and Q is 0.5, well, if I'm looking for the frequency of heterozygous pigs in the population, there's a formula, or really a part of the formula that I can use. But to speak back up to Paige's question, right? It's not P plus Q equals 1, it's the other formula, right? P plus Q equals 1 is adding together allele frequencies, right? The dominant allele frequency plus the recessive allele frequency. P squared plus 2PQ plus Q squared equals 1, the other formula, which you don't have to memorize, right? That's giving you the genotype frequencies, okay? So it does turn out that the part of that equation that refers to the heterozygous genotype is 2PQ. P squared refers to the homozygous dominant genotype, and Q squared refers to the homozygous recessive genotype. So let me just pause there for a second. Does this bring any new questions up? So the math here is really simple, right? We know P and we know Q, they're both 0.5, 0.5 times 0.5, 0.25 times 2, right, is 0.5, right? So of the 16 pigs, right, we expect half of them to be heterozygous, all right? So what becomes interesting, right, is that we're working with a population, right, 16 pigs, where we know how many are black and we know how many are pink, right? So where things get interesting is you could say to yourself, right, that 4 of the 16 pigs are black, right? That Q squared equals 4 out of 16 and Q equals 0.5 and P equals 0.5, right? But you know that there are 12 pink pigs, right? So what gets interesting is when you know a little bit more about the population, what you have to begin to ask yourself is, okay, well, and this is not meant to confuse you at all. This is meant to be very forthright and honest with you when it comes to these calculations, and it ties in really nicely to where we want to go with this concept moving forward, right? When you did these calculations, right? That's a terrible circle. I apologize, right? You might have looked at the population of pink pigs and said, okay, well, there are 12 out of 16 of the pigs that are pink. But I don't know if those pigs are homozygous dominant or heterozygous, because either of those genotypes could have led to pink color. It's the dominant characteristic in this particular population. And I can't look at a pig and know its genotype, right? If it's pink, it could be either homozygous dominant or it could be heterozygous, okay? So what we do know is that 12 of those pigs are pink. And we would say to ourselves, okay, well, if 12 of those pigs are pink, then we would expect some proportion of them to be homozygous dominant and some proportion of them to be heterozygous. We would say, okay, well, of those 12 out of 16 pigs that are pink, we might say to ourselves, okay, p squared, right, should equal the frequency of homozygous dominant pigs in the population, and 2pq should equal the frequency of the heterozygous pigs in the population. And we can do that math pretty simply, right? We know that p is 0.5. So p squared is 0.25. And 2pq, we just did this, right, is 0.5, which is nice because that's going to allow our math to work out, right? So we calculated q squared as 0.25. But Ben made an interesting point. He asked a really interesting question before. He looked at the pig population, he saw the 12 pigs, and what this would tell us, right, is that half of those pink pigs, right, half of the 12 should be heterozygous, right? And a quarter of those pink pigs should be homozygous dominant. You with me? That's what you'd expect. Okay. So you look at the population and you say to yourself, okay, well, before in that first question, we were trying to count, right? Calculate the number of recessive alleles in the population. So we would look at our black pigs, right? Our homozygous recessive pigs, and we said there were 4 of them. And each of those 4 black pigs brings 2 recessive alleles to the party. So that's a total of 8 recessive alleles. You with me? It's okay to say no. 4 black pigs. To be black, you have to be homozygous recessive. You have to have 2 copies of the recessive allele, the black allele in this case. 4 times 2 is 8. Okay. Of the remaining 12 pigs, right, we expect half of those 12 pigs to be heterozygous. So 6 of those pigs are expected to be heterozygous, right? But of those heterozygous pigs, they only bring 1 black allele, 1 recessive allele to the gene pool, to the population. So if you heard what Ben said, he came up with this answer of 14. But we calculated 16. Crap! Which answer is right? This is where Hardy-Weinberg equilibrium gets frustrating for students, right? Because you come up with these 2 different answers and you don't know which one's right. But it's the matter that the numbers are different that's important. Because if you come up with different values, it's actually telling you that the population you're studying, that you're investigating, is not at equilibrium. That it's being influenced by one of those mechanisms, like genetic drift, or natural selection, or immigration and emigration, or mutation, right? In a way that the frequencies of the alleles and the frequencies of the genotypes are not what you would expect. Okay? And that's why I chose to start with this problem, not to confuse you, but to show you that biologists are always making an assumption when they study a population's gene pool. And the assumption they make from the get-go, in fact, here, let's pull it up. Go back to my mouse here. The assumption that they make and I thought the Amoeba Sisters did a really good job highlighting this in their video. They even used the same language that I use, right? Is that to begin with, they assume that all of these conditions are in effect, right? They do what we did. They calculated P and Q, or we calculated P and Q. We found that they were both 0.5, and we found that we would expect at that particular point in time that if that population was at equilibrium, there should have been 16 recessive alleles and 16 dominant alleles. But when you actually go to explore that population and you find, oh my gosh, wait a minute, it's not 16 and 16, it's actually 14 and 18. That's telling you something. It's telling you that these assumptions that are required for equilibrium to exist are not being met. And that what biologists do next is try to figure out which of these requirements are being violated. And it could be more than one. And the race is on. And that population is studied over the course of time to figure out how it's being influenced, how its gene pool is changing. Because ultimately, that's what this is all about. We're trying to mathematically quantify evolutionary change over time by studying a population's gene pool over time. And if frequencies are changing, if allele frequencies are changing, it's a clear sign that the population is evolving. Now, why it's evolving is a separate question. It could be one or more of these requirements. They're not holding up. They're not holding up. And we got to figure out which of those, and there might be more than one, is actually influencing the population over time. So let me just pause there again. What questions do you have about this?
My question's not necessarily about this specifically, but it was about part 3. When you were doing it, you got 8 because it was like half of 16. But why were you using 16 instead of the full 32?
Because I'm basing it off of the assumption that the population is at equilibrium.
Okay.
Right.
So you're basing it off that there's like half and half.
Right. I'm trying to use the P and Q values, right, to calculate 2PQ, the formulas that we would use, assuming that all of these things, sorry, keep realizing you're in student mode. I'm sorry. I'm hoping you're seeing what I'm seeing, or at least you're clicking through to follow along. If and it's okay to tell me that I'm still in student mode, Mr. Bergeron. I can't see what you're seeing. Okay. These are the requirements that are highlighted in the Edpuzzle video, right? That the Amoeba Sisters describe. Okay. So if what you're calculating isn't actually what you're seeing, then that population isn't at equilibrium. And one or more of these requirements are being violated. And you might be asking yourself, so why are we doing this? I've got an 8th grader at home, right? She's studying algebra. I'm never going to use this. Why do I have to know it? So every teacher bone, muscle, and ligament in my body tightens. We know you're not going to use this. Why do I have to do it? Because it's about problem solving. It's about thinking. In the case of Hardy-Weinberg equilibrium, right? Yeah, we're using algebra, kind of, sort of, right? Really basic algebra. But that's not what's important. It's about the conceptual understanding, right? If the frequencies of the alleles are changing, the population is evolving. And we have to start somewhere. Right? The Amoeba Sisters use the term baseline. I love that. That's the term that I use, right? Our baseline assumption is that all of those conditions are being met. Even if they're not, right? We got to start somewhere. We calculate our frequencies, and then we look at the population. We track it. Are those frequencies changing? If they are, the population is evolving. It's not an equilibrium, right? It's a disequilibrium. If they're staying the same, the population is at equilibrium, and it's not evolving. And of course, along the way, we're looking for significant changes, not just numeric changes in frequencies. Right. All right. So we're going to take a break here in just a moment. But before we do that, what questions do you have for me or for the good of the group before we take our break? Well, let's do just about 3 minutes. So I've got 10:39 on my clock. We'll come back together at 10:42 and we'll try a few more of these practice problems before we sign off. Right? I'll see you in a few minutes. All right, if we could start making our way back together. So I think that it might be helpful to do one more together before we try to do some on our own. So I'm going to leave you in teacher mode, but take a look at this question. It's an AP question. These are all released exam items. So take a moment, read the question, and then ask any clarifying questions that you might have before we solve it together.
When it says like approximately 45%, would that be Q squared?
You got it. Well done. Ready to tackle this one together? Thumbs up if you think you're ready. Down to one other camera at this point. So can't really see you. So anything you can provide for me is helpful. All right. So Paige really hit the nail on the head, right? And I thought the Amoeba Sisters did a really good job with kind of highlighting, summarizing how you approach problems like this, right? You want to look for the frequency of the homozygous recessive genotype when you solve a Hardy-Weinberg problem, okay? Do not be tempted, right, by the homozygous dominant genotype frequency or even the heterozygous genotype frequency, because you're going to end up working with unknowns there. Like, it's classic for students to say, well, if I know the dominant frequency, right, then I know p squared plus 2pq equals that frequency. For the love of dog, folks, if you find yourself trying to solve for two variables, you're going down the wrong path. Okay, don't do that. Keep it simple. And absolutely, Paige is spot on. In this case, I'm not sure where the best spot to write this is. Q squared equals 0.45.
I kind of worked ahead a little bit, but I got that P and Q weren't equal. Does that mean that it's not at equilibrium?
No, it's a really good question too. When we say equilibrium, we don't need the frequencies of the alleles to be equal to each other, right? We're simply calculating them and asking, really assuming that that's the starting condition, right? That all of those assumptions for equilibrium are in effect. It's our baseline, our time zero, our starting point, call it what you will. And what we're going to do is at some later time point, we're going to come back to that population. We're going to recalculate those frequencies and ask the question, have they changed? If they've changed, the population is evolving, right? Due to some influence that we then want to explore further. If the frequencies are the same, well, then that population isn't evolving, right? And that somehow, almost miraculously so, that all of those factors are in effect. No natural selection, no immigration, no emigration, no genetic drift, right? No mutation, all of those things. Okay. So for right now, my calculator is my phone. It's probably the easiest way to do this, but you may have already done this. We want the frequency or the percent of the North American population that is homozygous dominant for the ability to taste. Well, that means I'm going to have to take my 0.45 and find Q first, right? And that means, if I can get it to fit, I hope you can see this okay on your end. The square root of 0.45 is 0.67. So to speak to Paige's point, that's going to give us a P that is not equal to Q. It's going to be 0.33. Okay. And since we're looking for the percent, the frequency, right, of the homozygous dominant individuals, well, that's going to be our P squared term. And no, you don't have to even memorize which symbol is which. They are all provided. Okay. Use your brains to solve the problem, not to memorize extraneous details. Okay. So in this case, that's just going to be 0.33 squared, right? Oops, I lost my calculator. Hold on. So clear, 0.33 squared is going to end up being 0.11. And as a percentage, right, that would be 11%. So you can choose how you want to express that. In the past, the College Board used to have this funky part of the exam where there would be calculations like this, and to answer the question, you had to bubble in the actual numbers that corresponded to your answer. They don't do that anymore. Well, I take that back. They were going to make the change last spring, and they threw out all the multiple choice questions. So in 2021, it would be the first year where they do it. But now they're going to have multiple choice answers that are based on the calculated value. So you're not going to have to fill in some nonsense bubbles to express your answer. One of the answers will be there for you to choose as part of a multiple choice question. Okay. You want to try one on your own before we wrap up? Okay. So there's several of them. And what I'll do first is I'll put you into student mode so that you can choose a question that makes sense for you. If you want to check your answer, I can't post the answer through Pear Deck. It's kind of a pain. But if you go to the Unit 3 notes on Classroom, you'll find the same questions. And in the speaker notes, I've added the answer. Okay, it's highlighted so you can find it. Okay, so take the next couple minutes and choose a problem to solve. And then you can check your answer when you're finished. And we'll wrap up here with about a minute to go. So take the next 4 minutes to solve a problem on your own. hopefully you had a minute to at least tackle one of the questions and then look at the answer. And I want to honor the time that we have left. It's not a lot. So I'm gonna take you out of student mode, and it's a quick drag your dot question. Didn't have a ton of practice time today, so really thinking about our next step and our next meeting. How much more practice would you like? A lot, maybe 1 or 2 more problems, or nah, I'm good. Let's move on. If you could just drag your dot, I would appreciate it. And once you've done that, you're welcome to sign off, and I will see everybody hopefully in a couple of days.
Thank you.
Thank you.
Thank you.
Mr. Bergeron?
Yeah.
I just had a question about the summative assessment. I wasn't able to like do the Google Drawing thing. Like it wouldn't let me upload it. So I just put it like in the classroom post. I left my like a picture of my drawing.
Yeah, that's fine.
That's fine. Okay. Thank you.
Yeah, you're welcome.
Hey, I'm really sorry that I haven't been able to get my lab in. I just messaged you. I've been trying to catch up on a lot of stuff, and it should be in by the end of today. I'm really sorry about that.
Ben, this is a ridiculous time for all of us. And if you encounter adults who are not understanding and empathetic, I am going to question their humanity right now. So please do the best that you can and let me know when you do have a chance to submit it so that I can take a look at your work. Okay. No penalties here.
Okay, thank you very much. Hope everything gets better on your end. See ya.
Thanks.